you know? You're a human, which means at some point in your life, a teacher handed you a piece of paper covered in letters pretending to be numbers and said, "Solve for X." You panicked. That panic is called algebra trauma, and today we're going to fix it because algebra isn't actually about X. It's about one thing: figuring out what's missing. That's it. That's the whole subject. Everything else is just fancier ways of asking, what number makes this true? So let's start with the raw materials. Numbers come in flavors. Natural numbers are your counting numbers, 1, 2, 3, the ones you used to count your fingers before you had better things to do. Add 0 and negatives, you get integers. Add fractions, you get rational numbers, anything you can write as one integer over another. But some numbers refuse to be written as a fraction, like pi or the square root of 2. Those are irrational. Not because they're bad at math, but because their decimals go on forever without repeating. Combine rational and irrational, you get real numbers, which is basically every number that exists on a number line. Anyway, back to letters. Why do we even use letters like X? Because sometimes you don't know a number yet, and writing the unknown thing every time is exhausting. So mathematicians said, screw it, let's use a letter, and X became famous for being professionally mysterious. A letter standing in for a number is called a variable. A number sitting next to a variable, like the 3 and 3x, is called a coefficient. And when you glue variables, coefficients, and numbers together with plus and minus signs, you get an expression. No equals sign, no drama, just a pile of math sitting there. Add an equals sign though, and now you've got an equation, a statement that two expressions are the same value. That's when things get interesting, because now you can solve it. Solving means using inverse operations to peel away everything that isn't your variable until it's standing there alone, exposed, like it just lost a game of strip poker to subtraction. Addition undoes subtraction. Multiplication undoes division. Whatever you do to one side, you do to the other, because an equation is basically a scale, and scales get mad if you only add weight to one side. Let's try one. 2x plus 5 equals 15. Subtract 5 from both sides. 2x equals 10. Divide both sides by 2. X equals 5. Congratulations, you just found the missing number, and somewhere a middle school teacher is proud of you. This is called a linear equation because when you graph it, it makes a straight line, and also because linear sounds smarter than the easy kind. Speaking of graphing, let's talk about the coordinate plane, which is just two number lines having an argument at a right angle. The horizontal one is the x-axis, the vertical one is the y-axis, and where they cross is the origin, which sounds like a superhero backstory, but is really just the point 0, 0. Every point on this plane gets an address, an x-coordinate, and a y-coordinate, written as an ordered pair. Plot enough points from an equation, and you get a graph, a visual diary of every solution that equation has ever had. For a linear equation, the graph is a straight line, and every straight line has a personality defined by two things: slope and intercept. Slope tells you how steep the line is, rise over run, how much y changes for every step x takes. A positive slope goes uphill left to right, a negative slope goes downhill, and a slope of 0 is just lying flat, refusing to commit to a direction. The y-intercept is where the line crosses the y-axis, basically where the line was born before it started climbing or falling. Put slope and intercept together and you get slope-intercept form, y equals mx plus b, where m is slope and b is the intercept. This one formula lets you sketch practically any straight line without plotting a single point, which is either efficient or terrifying depending on how you feel about shortcuts. Now, sometimes one equation isn't enough drama, so we throw in a second one, and now you've got a system of equations, two lines trying to coexist on the same plane. Solving a system means finding the point where both lines agree, where they intersect, because that point is the one pair of x and y values that makes both equations true at the same time. There's a few ways to find it. Substitution means solving one equation for a variable and shoving that answer into the other equation, like sending a mole into enemy territory. Elimination means adding or subtracting the equations to cancel out a variable entirely, like two roommates canceling each other's chores. And graphing means literally drawing both lines and seeing where they cross, which works great until the intersection point has decimals and your pencil starts crying. Sometimes lines never meet, running parallel forever, same slope, different intercept, no solution, eternally single. Sometimes they're the exact stacked on top of itself, infinite solutions, which is less a system and more a case of mistaken identity. Okay, moving past equalities, sometimes life isn't equal, sometimes it's just more or less, and that's where inequalities come in. Instead of an equals sign, you get greater than, less than, or their chill cousins, greater than or equal to, and less than or equal to. Solving inequalities works almost exactly like solving equations. Same inverse operations, same peeling away of layers, except for one sneaky rule. If you multiply or divide both sides by a negative number, you have to flip the inequality sign, because negative numbers are rebels who reverse the order of everything they touch. Graph an inequality on a number line and you get a ray instead of a point, a whole range of values that work, shaded in like a highlighter, went rogue. Now let's zoom into a bigger idea holding all of this together. Functions. A function is basically a very committed relationship between inputs and outputs, where every single input gets exactly one output. No cheating, no input getting two different outputs. That's called not being a function, and also probably grounds for a breakup. We write functions using notation like f of x, which just means plug x into this machine and see what comes out. Functions are basically vending machines. You put in a number, snacks come out, and if you ever put in the same number twice and got two different snacks, you'd smash the machine, which is exactly why functions have that one output per input rule. You can test if a graph is a function using the vertical line test. If a vertical line ever crosses the graph more than once, it's not a function. It's just a shape being greedy with outputs. Every function also has a domain, the full set of inputs it's willing to accept, and a range, the full set of outputs it's capable of producing. Some functions are picky eaters. You can't divide by zero, so if there's a variable sitting in a denominator, whatever value would make that denominator 0 gets kicked out of the domain entirely. You can't take the square root of a negative number either, at least not in the world of real numbers, so anything under a radical has to stay non-negative, or it gets rejected at the door too. Funcs can also get remixed. Take a basic function and shift it up, down, left, or right, and you're performing a translation. Add a number outside the function, it slides vertically. Add a number inside, next to the variable, it slides horizontally, but in the opposite direction you'd expect, which trips up basically everyone the first time. Because math loves a good plot twist. Stretch or squish a function vertically by multiplying the whole thing by a number, or flip it upside down by multiplying by -1, and you've got yourself a full toolkit of transformations, letting you take one basic shape and warp it into an entire family of related graphs without starting from scratch every time. There's also piecewise functions, which are basically functions with multiple personalities, behaving one way for certain inputs and a completely different way for others, stitched together with conditions like use this formula if x is less than 3, use that formula otherwise. Absolute value functions are a classic example, since they're secretly just a piecewise function that flips negative inputs into positive ones, which is why their graph looks like a perfect V, a straight line that changed its mind halfway through. Speaking of absolute value, solving absolute value equations means remembering that the expression inside those two vertical bars could have started out positive or negative and still landed on the same result, since absolute value strips away the sign entirely. So if absolute value of x minus 2 equals 5, you actually have two separate equations hiding inside one, x minus 2 equals 5, or x minus 2 equals -5, giving you two totally different solutions from one innocent-looking equation. Absolute value inequalities work the same sneaky way, splitting into two cases, except now you're also juggling that whole flip the sign rule from before, so pay attention or you'll end up with a set of solutions and no idea why hunts can also curve, twist, and do way weirder things, which brings us to polynomials. A polynomial is an expression built from variables raised to whole number powers, added or subtracted together, like x squared plus 3x minus 4. Each chunk, like 3x or x squared, is called a term, and the biggest exponent in the whole thing determines the degree. Degree 1 is linear, a straight line. Degree 2 is quadratic, a curve shaped like a smile or a frown called a parabola. Degree 3 is cubic, and it gets wigglier from there. Polynomials with one term are monomials, two terms are binomials, three terms are trinomials, and honestly after that mathematicians just gave up naming them and said polynomial, which is Greek for a lot of terms and I'm tired. To add or subtract polynomials, you combine like terms, meaning terms with the exact same variable and exponent, because you can't combine x squared with x any more than you can combine apples with the concept of Tuesday. To multiply polynomials, you distribute every term in one by every term in the other, which for two binomials gives you the beloved FOIL method. First, outer, inner, last, a little dance where every term gets to meet every other term at least once, like awkward mingling at a math party. Now here's where things get spicy. Factoring, which is basically multiplication in reverse, taking a polynomial and breaking it back down into the pieces that multiplied together to make it. Why bother? because factoring is the secret key to solving quadratic equations, the ones shaped like ax squared plus bx plus c equals 0. If you can factor it into two binomials multiplied together, and that product equals 0, then at least one of those binomials must equal 0, because the only way to multiply two things and get 0 is if one of them already was 0. That's called the zero product property, and it single-handedly does most of the heavy lifting in quadratic solving. But not every quadratic factors nicely. Some of them are stubborn, ugly, refuse to break into clean pieces. For those, we bring out the big gun, the quadratic formula x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. It looks like a magic spell because it basically is one. It works on every single quadratic equation ever, no exceptions, guaranteed. That little piece under the square root, b squared minus 4ac, is called the discriminant, and it's basically a fortune teller. If it's positive, you get two real solutions. If it's 0, you get exactly one repeated solution. The parabola just barely kisses the x-axis. And if it's negative, you get no real solutions at all, because you can't take the square root of a negative number without summoning imaginary numbers, which is a whole other adventure involving the letter I, where I squared equals negative 1, and yes, mathematicians really did just decide that's allowed. Combine a regular number with an imaginary one, like 3 plus 2i, and you get a complex number, which sounds intimidating, but really just means a number living on two axes instead of one, a real part and an imaginary part holding hands. Complex numbers don't show up on the regular number line because they're too weird for it. They get their own plane entirely, but they still add, subtract, and multiply using the same rules as everything else, just remembering that I squared quietly becomes negative 1 every time it shows up. Graph a quadratic and you get a parabola, a U-shaped curve with a highest or lowest point called the vertex, and a line of symmetry running right through it because parabolas are obsessed with balance. If the leading number in front of x squared is positive, it opens upward, a smile. If it's negative, it opens downward, a frown, which feels a little on the nose for how most students feel about quadratics. Let's talk exponents for a second because they show up everywhere. An exponent just tells you how many times to multiply a number by itself. X to the third power means x times x times x. When you multiply two powers with the same base, you add the exponents. When you divide, you subtract them. When you raise a power to another power, you multiply the exponents. Anything to the power of 0 equals 1, which feels like cheating, but is actually just the pattern holding steady. And a negative exponent doesn't mean negative, it means flip it into a fraction, 1 over that same thing with a positive exponent, because negative exponents are really just exponents that got sent to the other side of the fraction as punishment. Related to exponents are radicals, the square root symbol and its cousins, cube roots, fourth roots, and so on. A square root asks, what number times itself gives me this? A cube root asks the same question, but with 3 copies instead of 2. Radicals and exponents are actually the same idea wearing different outfits, since a square root is really just raising something to the power of 1/2. Simplifying radicals means pulling out perfect squares hiding inside, so the square root of 12 becomes 2 times the square root of 3, because 12 is secretly 4 times 3, and 4 is a perfect square that's been dying to escape. Now, rational expressions are just fractions where the top and bottom are polynomials, and they behave a lot like regular fractions, which means you can simplify them by canceling common factors, but only after factoring first, never before, because canceling terms before factoring is basically math heresy and will get you disowned by your teacher. You add and subtract rational expressions by finding a common denominator, same as regular fractions, and you multiply and divide them by multiplying straight across or flipping and multiplying, same rules, scarier looking letters. Let's talk about exponential functions for a second, because they're the opposite personality of linear functions. Where linear functions add the same amount every step, exponential functions multiply by the same amount every step, which means they start slow and then absolutely explode like a rumor or compound interest or a video going viral. They look like y equals a times b to the power of x, where b is the growth factor. If b is bigger than 1, it grows. If b is between 0 and 1, it decays, shrinking towards 0 but never quite touching it, because 0 is basically the asymptote's forbidden fruit, always close, never eaten. Which brings us to logarithms, the natural enemy and secret best friend of exponents. A logarithm answers the question, what power do I need to raise this base to get this number? If 2 to the power of 3 equals 8, then log base 2 of 8 equals 3. Logs are just exponents wearing a trench coat and sunglasses, pretending to be a totally different concept, but really just asking the same question backwards. They're incredibly useful for solving equations where the variable is stuck up in an exponent, because logs let you bring that exponent back down to ground level where you can actually deal with it. Okay, let's zoom out one more time and talk sequences. Ordered lists of numbers following a pattern. An arithmetic sequence adds the same number every time, like 2, 5, 8, 11, always adding 3. Basically the linear function of the sequence world. A geometric sequence multiplies by the same number every time, like 2, 6, 18, 54, always multiplying by 3, the exponential function's sequence cousin. Add up all the terms in a sequence, and you get a series. And yes, there are formulas for that too, because mathematicians really don't like adding things one by one if they can find a shortcut. And finally, let's talk about why any of this matters, because algebra isn't just letters for the sake of letters, it's a toolkit for describing anything that changes in a predictable way. Linear equations model steady growth, like a savings account earning a flat rate. Quadratics model things that go up and come back down, like a ball thrown in the air, obeying gravity whether it wants to or not. Exponentials model runaway growth or decay, like bacteria multiplying, or a radioactive substance disappearing over time. Every real-world pattern that repeats itself in a mathematical way can be captured, predicted, and solved using the exact tools we just walked through. Let's actually try one, because theory is nice, but application is where algebra earns its keep. Say you're launching a water balloon, and its height in feet after t seconds follows the equation h equals negative 16t squared plus 64t. That negative 16 comes from gravity, doing what gravity does, relentlessly pulling everything back down. To find out when the balloon hits the ground, you set h equal to 0, since height of 0 means splat. Negative 16t squared plus 64t equals 0. Factor out the common term, negative 16t times the quantity t minus 4 equals 0. Using the zero product property from earlier, either negative 16t equals 0, meaning t equals 0, which is just the moment you launched it, or t minus 4 equals 0, meaning t equals 4. So the balloon splats exactly 4 seconds after launch, and somewhere, a sibling is furious. Want to know the peak height instead? That's where the vertex of the parabola comes in, sitting exactly halfway between the two solutions we just found, at t equals 2. Plug 2 back into the original equation, negative 16 times 4 plus 64 times 2, and you get 64 feet, the highest point the balloon reaches before gravity remembers it exists. This is the entire pattern behind projectile motion. Profit maximization, area optimization, basically any situation where something climbs, peaks, and falls, algebra just quietly running the show in the background.